For our capstone project, we are designing an automated wheelchair canopy. The following video explains our concept generation process and presents the final concept that we selected to move forward with.
Hello, my name is Adithu Malapalli, and today I will be covering our motivation for this product, the problem definition, our potential impact, and a market analysis of similar products. So our team observed that individuals who use motorized wheelchairs and scooters as mobility aids are often susceptible to being unprotected from adverse weather such as rain or snow. Traditional solutions such as umbrellas or canopies are often cumbersome or impossible for the user to deploy by themselves, and they must therefore rely on assistance from others to do so, as you can see in the photograph on the right. As a wheelchair user myself, I have encountered this type of situation countless times and have been unprepared to handle such weather on my own. So our goal is to create a solution that protects motorized wheelchairs and their users from adverse weather and can be deployed without assistance from others. A successful design will hopefully provide protection, peace of mind, and independence to those with limited mobility in poor weather conditions. Some current products on the market, like the ones shown at the right, are not automated, may lack adequate protection, are expensive, or may require the help of an additional person to deploy. Our solution would have to address these shortfalls in order to be viable.
Hello, my name is Aaron Seldowitz, and I will be talking about how we developed our customer requirements. So with the idea of the product in mind, we actually interviewed a single person to figure out some of the initial requirements we would have for the product. And after figuring those out, we sent out surveys that had a lot of these requirements on them and gathered information from people in the DMV area who were in wheelchairs, kind of what they would like to see in a product like this. So we got about 22 respondents, and from those respondents, we figured out a lot of our initial concerns included the weight, the form factor, area of coverage, and amount of electronics in the product. So we were then able to compile a more formal list of customer requirements, and we put them in 3 different classifications. So we have some more expected requirements, stuff like it has to be easy to operate. If it isn't easy to operate, the customer won't want to use it. And waterproof, it obviously has to be waterproof. The idea is that we keep our customers dry with this canopy. And then we have some more spoken customer requirements, stuff that they kind of voice their concern, and we kind of voiced it throughout the process to figure out, is this something they would want? And this includes, covering the entire person and the chair, not obstructing the view of the user, not everything we originally thought of, but stuff that was brought to our attention. And then we have some more unspoken requirements. And some of this is like rain can't collect on the top and it can't weigh down the chair. This is stuff that we didn't consider, stuff that the customers brought to our attention, and it's something we don't have to particularly design for. However, it is something we have to keep in the back of our mind with each design iteration. So we combined a lot of our requirements. A lot of them were kind of the same thing, just written differently. So we combined those to make one cohesive requirement. We added the unspoken requirements, and we were able to remove a lot of the more subjective and lesser ranked requirements. So by ranking, 1 to 5 in the survey, we were able to see what our customers would want to see, and then according to each requirement, compared to each other, we were able to rank how important they were on a scale from 1 to 10, 10 being the most important.
Hello, my name is Nathan Raver, and today I will be covering the relevant design constraints, the design targets, and the decision criteria. For the relevant design constraints, given our CTQ CRs, we came up with design constraints that had the ability to inhibit our goal to meet all customer requirements. For example, in order for our design to be universal, we will have to avoid any specific mounting methods that would only lend itself to a specific chair used, and we will have to avoid more complex geometries that would only fit on certain chairs. In order for the product to remain within the footprint of the chair, we not only had to explore the varying powered chair widths, but also door codes that tell us how wide each doorway is, and that way the product wouldn't be able to inhibit everyday life for the user. The main human input in this product would be the signaling of the actuation, which is how the user operates the canopy. In order to make this easily operable, the actuation control must not only be in reach of the user, say if they have limited arm mobility, but also must be easy to push/activate. To keep the cost down and make the product more affordable, we decided that we should avoid using expensive components because although they might make the product easier to design and use, we don't want to make this another expensive product. Given that our product will be powered, we also need to come up with a power supply that won't affect the current use of the chair, because we don't want this product to drain the power of the chair and become a nuisance for the customer. We defined our design targets as methods to meet some of our major CTQ CRs. For example, one of our main goals is to use basic components to not only keep the cost down, but to mitigate any complicated failures, because the more complicated something is, the more complicated its failure methods can be. We also want the product to cover the user when deployed, but be as invisible as possible in collapse. So we want our deployed to collapse area ratio to be high. As mentioned before, we want to avoid complicated designs, not only to keep the chair universal, but to give the user the opportunity to fix any small failures instead of having to pay a professional to do so. Finally, we want our product to be not only durable, but relatively lightweight to avoid weighing down the chair. So we need to find a happy medium between the strength and the weight of components. For our pew chart, we decided to use all of the engineering characteristics from the House of Quality as our decision characteristics, with corresponding weight next to each one. As you can see, we have footprint when collapsed, which we want to be at a minimum, surface area when deployed, which we want to be at a maximum, volume used by electronics, which we want to be as small as possible to allow it to fit on all powered chairs, water resistance, which is important when designing umbrellas and canopies, the weight, which, as mentioned earlier, should be as low as possible to avoid draining the chair battery capacity, so our product won't have to be charged every day and it will be able to operate on command, strength of material, which will make this product worthwhile and last longer. We want it to be able to survive wind gusts, and the center of gravity, which is important for the deployment of the canopy. We also want it to be able to stay deployed and not fall down due to its weight. While some are determined to be weighted higher, all the characteristics will have an impact when distinguishing solid concept designs. In addition to that list, cost also becomes a decision characteristic. Cost is defined as how affordable the product will be for consumers compared to the price of the datum, which was $180 for a permanently attached manually deployed canopy.
Hi, I'm Kelsey, and I'm going to talk about our initial concept generation, and later I'm going to talk about the analytical hierarchy process. For our initial concept generation, each team member individually came up with 10 different concepts, so we had 60 initial ideas for our design. After eliminating repeats and impractical concepts, as a group we were able to narrow our remaining concepts down to the 5 that we collectively thought were the best solutions to our problem. We put these 5 concepts in a pew chart using the DSCO Power Wheelchair Canopy as our datum for comparison. After analyzing the results, we were left with our final 3 concepts, which are highlighted on the pew chart: the Carriage Canopy, the Retractable Awning, and the Rigid Canopy with Servo.
My name is Denton Piet, and I will be briefly discussing the general functions of our 3 final concepts. Concept 1 is inspired by a stroller or carriage canopy and would utilize a single point of actuation in order to deploy over the head of the user from a collapsed storage position. The canopy would be constructed out of some flexible material that would allow for a compact storage capability. Concept 2 takes inspiration from patio or motorhome awnings that utilize a rolled sheet of material that can be deployed in a linear fashion. The actuating arms extend outwards and unroll the material to protect users from adverse weather conditions or to provide shade. The third final concept in consideration is the servo-controlled rigid canopy. As opposed to the previous 2 concepts, this device would employ a single rigid sheet of material that would be position controlled by 2 servo motors.
We analyzed our final 3 concepts in an analytical hierarchy process. We created one 9x9 matrix that weighed all of our decision criteria, including cost, against each other. We also created 9 3x9 matrices to compare our final concepts to each of our decision criteria. From these matrices, we were able to get the averages of the normalized weights for the decision characteristics, as well as the averages of the normalized weights of the 3 concepts compared to each decision characteristic. These final averages are shown on the slide. Finally, from these averages, we were able to find the aggregated weights of the concepts. From the third chart on the slide, you can see that the carriage canopy had the highest aggregated weight at 0.37, the retractable awning was a close second at 0.346, and the rigid canopy with Servo had the lowest aggregated weight at 0.28.
This is Shannon, and we chose to go with the retractable awning design. When activated with the actuation method, the supporting pneumatic rods telescope upwards past the headrest of the wheelchair. The motor rotates clockwise, and the opening pneumatic rods telescope, moving the awning spool rod forward and unrolling the canopy. The canopy extends over the user's feet when fully deployed. When the user is finished using the canopy, he or she can activate the spring-loaded canopy retractor to roll the canopy back to its original position and collapse. All electronics are located under the seat and will be covered by the awning to protect them from any water damage. Although the carriage design had the higher weighted average after the HAP analysis, 0.37 to 0.346, we still decided to go with the awning concept because it has a much smaller footprint when collapsed. This was a highly rated design characteristic, and we figured that it would be the best choice for our final concept design. With further work in embodiment design, discussing manufacturing processes, and prototype planning, we expect to have developed a well-rounded product that will cater to all of our customer requirements and engineering characteristics.